You ever wonder why some things happen in the blink of an eye, like an explosion, while others, like an old iron nail rusting, take, well, forever? I mean, they're both just chemical reactions, right? But they're playing by totally different clocks. Today, we're going to dive into why that is, and we'll use two pretty famous shipwrecks to figure it out.
So check this out. On the left, you've got the Titanic. It's been sitting at the bottom of the ocean for over 100 years, slowly rusting away. That's a chemical reaction. And on the right, that's the shipwreck of the Kaizen. Its cargo of sodium hit the seawater and boom, a massive, violent explosion. Also a chemical reaction. So what in the world is the difference here? How can you have one reaction that's a slow-motion decay and another that's a fiery, instantaneous blast? Well, it all comes down to a really cool branch of chemistry called chemical kinetics. This is the science that's all about the speed of reactions. It digs into the how and how fast of chemistry. It's basically the official rulebook for the chemical racetrack.
So here's our game plan. We're going to start with our two shipwrecks, then figure out how we actually measure reaction speed. After that, we'll get into the rules that control the whole race, uncover the secret step-by-step path that reactions take, see how we can actually hack the process, and finally, bring it all together to see how kinetics is, well, literally everywhere.
Okay, first things first. If we want to talk about speed, we have to know how to measure it, right? So how do chemists actually put a number on how fast a reaction is going?
They use something called the reaction rate. And honestly, it's a pretty simple idea. You just measure how quickly your starting materials, your reactants, are getting used up. Or you could track how quickly your final stuff, the products, are being made. It's kind of like measuring a car's speed in miles per hour, but instead, we're talking about molecules per second.
And this graph here, it tells that story perfectly. You see that red line going down? That's our reactants disappearing over time. And the blue line climbing up, that's the product being created. The really cool part is that the steepness of those lines at any given moment tells you the exact speed of the reaction right then and there. Now, it turns out that these reaction speeds aren't just all over the place. Nope, they follow a very specific, predictable set of rules. Think of it like a recipe. So let's check out the instructions that run this whole chemical race. Every single reaction has what's known as a rate law, and that's just a fancy term for its specific set of instructions. It's a little math equation that tells you exactly how the amount of stuff you start with affects the overall speed. And trust me, this isn't just for textbooks. Understanding rate laws is how chemists control everything, from how fast a painkiller works in your body to how long food can last on a shelf.
And this is where it gets interesting, because the rules can be different. For some reactions, which we call first order, the time it takes for half of your material to react, that's its half-life, is always the same. Doesn't matter if you start with a ton or a tiny bit. But for other types, like second-order reactions, that half-life actually depends on how much you started with. The big takeaway here is that the recipe isn't one size fits all. The rules of the race change for every reaction.
Okay, so we know how to measure the speed, and we know there are rules. But what is actually happening down there, at the level of individual molecules? Let's pull back the curtain and look at the reaction's secret path. You know that clean, single-line equation you see in a chemistry book? Well, that's kind of like the movie poster. It gives you the basics, but it doesn't show you the whole story. The real story is the reaction mechanism. It's the entire sequence of tiny, individual steps, molecules bumping into each other, breaking apart, and rearranging, that all add up to the final result. A great example is how ozone breaks down. The overall reaction just says 2 ozone molecules become 3 oxygen molecules. Simple enough. But the mechanism shows it's a 2-step dance. First, one ozone molecule just splits apart all by itself. Then, the oxygen atom that broke off goes and collides with another ozone molecule. It's this hidden choreography that's really running the show. So, if a reaction has a bunch of steps, which one actually sets the final speed? It's always the slowest one. We call this the rate-limiting step. The best way to think about it is like a bottleneck on the highway. It doesn't matter how fast the cars are going on the rest of the road, the whole flow of traffic can only move as fast as the cars squeezing through that one narrow lane. This is probably one of the most crucial concepts in all of kinetics. So, knowing all this, can we actually do anything about it? Can we control the speed? Can we hack the reaction? Oh, absolutely. And one of the most powerful tools in our toolkit for doing that is something called catalysis. In the biological world, the undisputed champions of catalysis are enzymes. And as this quote says, they're basically specialized proteins that living things create to speed up very specific reactions. Everything from digesting the food you just ate to making copies of your DNA, it's all happening because enzymes are there, making it happen fast enough to support life. And they do it with this incredibly elegant two-step trick. First, in a really fast step, the enzyme grabs onto its target molecule. Then comes the second, slower step, the rate-limiting step, where the actual chemistry happens, the product is made, and the enzyme lets go, completely unchanged and ready for the next round. The real magic here is that the enzyme doesn't just make the old path faster, it creates a brand new, much easier, and way faster shortcut for the reaction to take. So, as we've seen, from the murky depths of the ocean to the tiny cells inside our bodies, chemical kinetics is this invisible force that's setting the pace for pretty much everything. Let's do a quick flyby of what we've uncovered.
All right, so we started by figuring out how to measure speed itself with the reaction rate. Then we saw that speed isn't random. It follows specific rules called the rate law. We took a peek behind the curtain at the secret step-by-step journey, the mechanism, and found out that the whole thing is controlled by its slowest part, the rate-limiting step. And finally, we saw how we can use catalysis to create a shortcut and speed things up.
So the next time you see a piece of metal rusting, or watch a cake bake in the oven, or heck, even just take a breath, you are witnessing the principles of chemical kinetics in action. It's the invisible director of the entire chemical world. So my question for you is, what everyday reaction are you going to see in a completely new light now?